Ooh, So welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie DeRomalar and I'm the Executive Director of the Observatory. And we're so honored to have Dr. Thomas Greene come back. He actually was here, I think it was right around this time last year, October, November, before the James Webb launch. So I'm really eager to hear kind of post launch information. And I'm going to introduce him in a minute, but also wanted to just remind you before we start to keep yourselves muted. If you have questions, you can go ahead and put them in the chat and we'll either get to them at the end of the presentation or, there might be a chance here or there to have them in the middle of the presentation, but please put them in the chat. Also, just to introduce Robert Ferguson Observatory, I see a lot of familiar faces and names here, but for those of you who are not familiar with us, we are run by the Valley of the Moon Observatory Association. It's a 501(c) nonprofit. And we've been around for about 25 years and are truly a public observatory. So kind of by the public for the public, while a lot of observatories are run by educational institutions or government agencies, anybody who is interested in astronomy or looking at the stars is welcome to come to some of our star parties and events and look through our telescopes, or even learn how to operate them themselves if they go through our volunteer training program. So as you can imagine, it's a really wonderful resource for the community, for students, educators, etc. We are almost all volunteer run and serve about 9,000 visitors annually. And the observatory is located in beautiful Sugarloaf Ridge State Park in Kenwood. We have a lot of, as you know, public star parties, events, outreach programs. We do classes, focus nights. We also do a bunch of other programs for the community, such as our Striking Sparks program, which has actually been around for 37 years, predating the observatory. It was started by Robert Ferguson, and that awards telescopes to students in Sonoma County every year. And I'm actually going to just bring up a little picture from our last. Hopefully you all see that. That is from our last Striking Sparks award ceremony. And this is Cecilia, Zoe, and Ruby on the right hugging her telescope. So we are doing that actually in, I think, February, the applications end. So just want to put that out there that we do some amazing programs. Stop sharing here for a sec. Sorry, letting more people in. All right. Speaking of our volunteer program, we actually have a new volunteer training starting at the end of this month. We only offer it about 3 to 4 times a year. So if you are interested, you can go to our website, rfo.org, and under the Join and Give heading, there's a volunteer application that you can fill out. It's just a simple application to basically let me know that you're interested and give you some more information. And that the first session of that training starts next Wednesday, I believe that's the 26th. Membership is also a great way to support the observatory while getting some member benefits. Our members attend public star parties for free and get 20% off discounts on our other classes and retail store. All right, just muting somebody there. And then lastly, just wanted to mention that we have kept the presentations in our speaker series for free to align with our mission of offering educational-based astronomy programs to the community. That being said, if anybody is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, or even, for example, sponsoring one of our Striking Sparks telescopes for these kids, that would be wonderful. And that can also be done through our website, rfo.org. When I get a moment, I'll put the direct link in the chat. So now, without further ado, I wanted to introduce Dr. Thomas Greene. Like I said, I'm so honored that he was willing to come back and speak to us today. Thomas Greene is an astrophysicist in the Space Science and Astrobiology Division at NASA's Ames Research Center. He conducts observational studies of exoplanets and young stars and develops astronomical technologies and instrumentation. Dr. Greene is a co-investigator on the NIRCam and MIRI science instruments of the James Webb Space Telescope and serves on the James Webb Users Committee. While at NASA Ames, he has served as the director of the Ames Center for Exoplanet Studies, project scientist of the SOFIA mission, and chief of the astrophysics branch. Before joining NASA, he worked at the Lockheed Martin Advanced Technology Center on NASA astrophysics missions. Prior to that, Dr. Greene was on the faculty of the University of Hawaii, where he was a support astronomer and later director of the NASA Infrared Telescope facility. He received his Ph.D. in astronomy from the University of Arizona. So without further ado, I will pass the baton to you, Dr. Greene.
Wow, great. Thank you, Stephanie, for that great introduction. And I'd like to thank everybody for coming to this talk. I really enjoyed the talk I gave, I think a little under a year ago. I think it was like early November, like you're saying, Stephanie. And I thought that it was a really well presented, well-run show, and all you folks asked some great questions. I was hoping that I could come back, and I'm really happy that things worked out, because James Webb was a little bit of a nail biter, and here I am. I'd like to for the next hour show you share a little bit of information about the observatory and also its science that has come out. So are we looking good there, Stephanie? Can you see the screen?
It looks perfect. Yep, looks great.
Excellent. Okay, so without further ado, I will go and start. So why would you put a telescope in space? It's really hard. You have to make something that's almost indestructible. You can't fix it if it breaks. And the rockets are only so big, and it's hard to get things up there. Well, there's sort of like, I was thinking about this, and there are kind of like three major reasons. And let me see if I can get a pointer here. Well, the sky is darker in space. We don't have scattered light. You folks see that, right? If you go outside, if you go to the I know the Robert Ferguson Observatory is a pretty dark site all in all, but you probably still see some light. And all from our houses, I bet we all see light. And it's the atmosphere that's scattering that. Also, the atmosphere limits what colors we can see. And that's what wavelengths of light. And also, space can be very stable, and I'll say a little bit about that. A very stable temperature, and we could also have more nighttime. So NASA actually has been putting telescopes in space for a while. There are a series of 4 observatories started in the 1990s that saw in different wavelengths, so different colors. There was this gamma ray observatory that's not here, so that's really the shortest wavelengths. And Spitzer worked in the infrared. Chandra is still flying. It works in X-rays. And Hubble, as we know, takes beautiful visible pictures. It goes a little blue visible, and it goes a little red visible also. And this is just to give some grounding here for the electromagnetic spectrum and where our eye sees versus what else is out there. So what we can see here is whoops, let me, I managed to open a window here. So the eye is pretty limited. It only sees about a factor of 2 in wavelength. From the bluest blue that we could see, which is something like a little under 400 nanometers. So how big is a nanometer? Well, it's 1 billionth of a meter. So that's pretty short for measuring the actual wavelength at which the light oscillates. All the way up to about 750 nanometers. And that's like the reddest red that we can see. But there's ultraviolet light that goes bluer than what we can see. And you get into these gamma rays, X-rays, and you go longer, you get into this more infrared light, and then microwave and radio. So these microwaves are actually get to be like millimeters. So you can start to even think about how long they are. And this is where Hubble sees. It sees, again, a little bluer than what we can see with our eyes, and also a little redder. It goes into the near infrared. Webb sees from pretty much green in our eyes all the way out to way red, to something like almost 20 times longer than, or more than 20 times longer than what our eye can see. And Spitzer was an infrared observatory that went even longer. And why would we want to do that? Well, we can see things in the infrared that we can't see in the visible. So these are just some familiar animals that we know and love: meerkats and a crocodile. So that's what they look like in visible light. So and we see them by the sun's rays are reflected by them, and they have colors based on what wavelengths of the sun are absorbed versus what's reflected. Now, if we go to the infrared, we see there's more going on here. We actually see that the meerkats are glowing, so they're bright. The white is bright here in the infrared. That's because they're warm inside, and infrared radiation is heat radiation. So they are actually emitting an infrared light. And but we look at this crocodile, it's really faint because it had just been in a cool pool of water. So and it doesn't have much infrared radiation. So you can tell temperature. That's one thing you can see by looking at things in the infrared. Also, we can see through dust in the infrared. So pretty famous space picture here. This is a Hubble visible light image of the Messier object. This is M16. The Space Telescope comes up with all sorts of catchy names. I think they call this Pillars of Creation. You may have also heard about it this week. So this is a visible light image. There are all these young stars forming in this Messier object, which is it's a nebula where stars are forming, and these are bright young stars, and there's still dense dust nearby. And once you look in the infrared over here, and this is with Hubble, it's a near infrared image. This is about maybe 2 times longer than what the eye can see. It's about as long as Hubble goes. And you see that there's this bright star here that you just can't see in the visible light, but you can see it's in the infrared, and it's forming inside of this dust. And you go to even longer wavelengths, like Spitzer, you can see that the dust even glows. So the dust has some temperature because it's absorbing light from the stars. This image, I think, just came out yesterday, or maybe the day before. This is a new comparison, what Webb sees here for the same M16 field, these pillars of creation. And this is sort of near to almost mid-ish infrared, out to about 5 microns. And you see that like there's this whole clusters of stars here that you just can't see in visible light. So there's just a lot more information, a lot more stuff going on. And it's also very sharp, which is something that you could see there. This shows an animation of going from visible light there to infrared here of a dark cloud. And there's a young star in the dark cloud. And the star, young stars frequently have these jets. And the jets send radiation and also gas out on a preferred axis. So this jet is moving towards us, and there's another one moving away from us. And you can't see the one that's moving away from us until you look in the infrared. And you see all these other young stars that are forming in this dark cloud. To give you an idea, the infrared and radio regime has about half of the light of the universe, and the visible and the bluer and ultraviolet light and X-rays, that has about half the light in the universe. So you're missing a lot of information if you're only looking in visible light and shorter wavelengths. I like this picture. So this is M51, right? I know a lot of you have seen this. This is the satellite galaxy. One interesting thing, this is the visible image over here. And you see wherever there are these dark dust lanes in the visible, and they become bright in the infrared because in the dust is where the young stars are forming. It's just the dust is obscuring it from our view. And so there, again, more stuff happening there. Another reason to look in the infrared is because of when objects move away from each other, their light actually shifts to longer wavelengths. So visible light can become infrared. So we know the universe is expanding. You know, its expansion has been measured pretty well, and early universe, if these galaxies and stars were emitting invisible light, they're moving away from us very fast, like very close to the speed of light for the early universe. And the wavelengths or colors of their light can be stretched by like 10 times. So something that is visible, so let's say like a hydrogen alpha line, you may have hydrogen alpha filters. You may have seen the sun in hydrogen alpha, and that's like it's like 650 some nanometers. That goes shifted out to 10 times longer. So like 6.5 microns, which is definitely the infrared. So you won't see things in the early universe unless you look in the infrared. So that was some of the motivation for just kind of the tech of what James Webb could see. And we knew that there were some big problems that a sensitive infrared telescope could address. We actually started working on science case for James Webb. I think I remember it was like early 1998, so almost 25 years ago. And we knew that some of the most interesting science would be things we hadn't thought of yet, but we knew if we made a capable observatory that could do significantly address big problems that have been around for a while, then it could probably do other things as well. So we came up with these 4 science themes, looking at the first galaxies that formed in the universe after the Big Bang, try to understand what they are and understand then how they evolved to become present-day galaxies like our Milky Way that's really well structured. And another science theme was studying newborn stars and planets. We've had some pictures of how stars form, but and the planetary systems, but we still have a lot of questions. And then also be able to understand planetary systems better, both in our solar system and elsewhere. And this one sort of got added around 2006, once we realized that exoplanets were a big deal. You know, exoplanets were only first discovered around normal stars in 1995. So it took a while for us to realize that we really needed to get them into Webb. So let's go through some examples of the different science themes here. The first one is this first light. So these are the first galaxies that formed. The idea is that the Big Bang happened 13.8 billion years ago, and the universe formed. It was very, very hot, very, very small. And it took about almost 400,000 years for it to expand and cool enough for atoms to form, and that's for the electrons to combine with protons to form hydrogen atoms. And then once that happened, stars formed, and gravity could pull the atoms together. Stars could form, although we're not quite sure how, because the early universe was just about all hydrogen and helium, a little bit of other elements. And what we have today is many more heavy elements. We understand star formation better today, but it's harder to cool the gas without those heavy elements. But at some point, we think these early galaxies formed, so stars formed in these organizations, and then their light starts to ionize all the neutral hydrogen that's around there. So basically, it's you have enough high energy light for it to break apart the hydrogen atoms. And then these proto-galaxies, these first groups of galaxies, we believe then started to merge with each other. People have worked on all this through simulations, also looking at, we can see data back to about here with Hubble, things about 600 million years after the Big Bang. And present day, you can see for yourself. If you go to the Robert Ferguson Observatory or your own telescopes, you can see nearby galaxies in the Messier catalog and New General catalog, etc. If you look at a point in space, let's say look outside of the plane of the Milky Way, just so it doesn't get too crowded, you'll see a big pileup of things at all ages. So we see well-formed galaxies that are nearby. We see things that are older and haven't quite developed the spiral structures yet. And we see these proto-galaxies. And at some point, we can't see further back because of all the scattered light and from the atoms that haven't formed yet. So the idea is, if you observe long enough, you'll be able to sort of get a bit of a sequence of these different galaxies. So this is what James Webb sees, if you look at a deep field, so this I think was about, well, it's a little, it's about 10 hours in multiple filters. And this is one of the first images that was released in July. These bright fuzzy things, this is a galaxy cluster. That's the SMACS cluster. It's about 5 billion light years away. So it's not really in the early universe, but it's pretty far away. But what it's doing is it's amplifying light behind it. All these weird shapes, and you see that it looks like these shapes are sort of concentric, and there's a center. Yeah, it's centered on this bright cluster of galaxies, because these are background galaxies whose light is being amplified and distorted by the mass. So the mass of this cluster is acting like a lens. So this is gravitational lensing. It was predicted by Einstein. It has been seen usually on smaller scales with Hubble and other telescopes, but it's amazing. So what it can do too is you can use a foreground cluster of galaxies, use the mass to amplify what's behind it and be able to get more information, makes them brighter. And here is, shows that with the power of Webb, not only can we take pictures like that, but there's another instrument, it's a spectrograph, where you can choose which objects that you want to divide into spectra. So you can actually divide into different wavelengths here. So these are the images of objects which were selected based on their colors, because they're observed in different filters. So ones that are really red, looks like their light is being emitted at very long wavelengths, were observed here. And this one looks like these are like a visible hydrogen line. I think that's H beta, an oxygen line, H alpha here. So this has got about a redshift of 3, because these wavelengths are shifted by about 4 times longer than the rest wavelengths, and all the way up to like a redshift of 8 here. So we can actually see kind of how far away they are based on these redshifts. So the redshift gives us velocity. It's just like the Doppler effect. If you go down to the train tracks and you hear the train go by, the pitch the pitch changes as it goes by, and that's what's happening here due to the motion of the universe. And things that are moving faster from us are further away. So we can convert these wavelengths into a speed and then into a distance. So also, by looking at a field of galaxies, or you could look otherwise too, we want to again understand how we go from these very early galaxies that we think weren't very big. They're probably on the size of what globular clusters are now. Globular clusters are pretty old, right? I mean, they're over 10 billion years old. So they're not that much younger than the universe in a lot of ways. And then they interact, start to form spiral arms, etc. So this is sort of like the picture we think what happened. So, and we have been able to see down to about here with Hubble, but we haven't been able to see past there. Done simulations to figure out what to expect. So this is an image of the James Webb sees of interacting galaxies. You may recognize this as Stephan's quintet. Actually, this looks pretty good for Stephan's quintet. If you ever looked at it, it looks pretty faint if you look at it through like one of our telescopes, something that's like a half-meter telescope or something. So it turns out this galaxy here is not physically interacting with these other ones. This one's actually a foreground one. It's about 40 million light years away. These are like 200, 250 million light years away. And you see these two have already interacted. They've gotten, they're spiraling in. And then this one and sort of these two together are interacting. This red light there, this is again infrared light that you can't see, and it's lighting up all this dust there, because where these two are banging into each other is where stars are forming. So and so this is how galaxies coalesce, how spiral arms form, and stars form in those spiral arms. This is another image of a galaxy that has gone through some interactions. It's the Cartwheel galaxy here, and it's got 2 rings, and it looks like there have been collisions with another galaxy. There's this one here, and then there's this outer one there. Okay, stars and planets. So before Hubble, we pretty much knew that stars had to form in disks. Actually, I think Laplace put this position forward in the 18th century. And but it's just a simple conservation of angular momentum, that if you have things that are sort of randomly rotating, there's going to be one preferred direction, and gravity will collapse perpendicular to that direction, because angular momentum makes it difficult for gravity to collapse in the direction that things are rotating. So Hubble actually showed us images. This is like an artist concept, but the Hubble images weren't too different from this. And what we'd like to see with Webb, though, is actually what's in these disks. What is the dust made out of? What kind of gas? What sort of ices and molecules are there? Are any of these important for life? Because this is how solar systems assemble themselves. So we can see what raw materials are there. This is another star formation region, Hubble in visible and infrared light. Again, the dust is where all these young stars are forming. And similar to those pillars of creation that showed earlier. Now, this is a James Webb image. You may have seen this. This is also another one from July. This is the Greene Nebula, and it's pretty impressive. So what's happening here is these are all bright young stars that have formed out of this dust. They have enough radiation so that they have basically vaporized the dust. They've blown the dust apart. And what they're doing here is they're sort of etching a shoreline of with the radiation from these stars, and this is the cloud out of which they were born, and they're still bright young stars like these here that are forming within this gas. So this is a mostly near infrared image, and some of these tendrils and stuff are actually sort of chains of molecules, these polycyclic aromatic hydrocarbon molecules. This is about 9,000 light years away, so it's in the Milky Way. Okay, planetary systems and the origin of life. I think I'm going to have to switch pointers here to get. Let me see if I can do a pen here. Oops. Well, I knew how to do this with a previous pointer options. Let's see here. All right, so this is this demonstrates the transit technique, and most of the planets we know about, there are over 5,000 known planets around other stars now, have been discovered with this transit technique. Most of them discovered with the Kepler mission. Kepler discovered over 3,000 planets, and this is when we get lucky, and we're looking at a lot of stars, and things are lined up. So a planet in its orbit moves in front of the star, and the star gets about 1% dimmer. So that's what this graph is here, when the planet moves in front of it. And we want to use the same technique for actually studying the atmospheres of the planets, because when the planet moves in front of the star, there's a very thin little bit of atmosphere that we can see through. We can actually see the star's light through the edge of the planet, and see how the planet's atmosphere changes the star's light. It's a very subtle effect. It's about 1% of the actual dimming of the star that the planet does. So that's about only about 1/10,000th of the light of the star at best. There's some good systems for investigating this. You may have heard about this TRAPPIST-1 system. This is only about 40 light years away, and it's pretty incredible because there are 7 small planets that are similar to the terrestrial planets in our solar system, and they're more or less in the habitable zone. Now their star is a lot smaller than the sun. It's about the smallest star you can have that's actually burning hydrogen and not a brown dwarf. This shows the TRAPPIST planets, which have the creative names B, C, D, E, F, G, H, like pretty much all planets do. And it shows here is sort of how much light they get from the host star compared to Earth, where Earth is 1. And so you see D gets a very similar amount of light. And this shows the density, or the, which is pretty much a surrogate for the mass also, because they're made out of the same stuff. So we have things very similar to Venus, things not too unlike Earth. This other one's a little hotter than Venus. I actually have some observations of this one coming up in less than a week. And all of these are going to be observed in the first year alone of Webb. And what are we looking for? Well, we're looking for different atoms and molecules in their atmospheres, and through this transit technique for the most part. A big one is carbon dioxide. You see that Mars, Earth, and Venus all have carbon dioxide. This is this is like the light spread out, and this is pretty far in the infrared. This is 15 microns, so that's about 20 times longer than what the eye can see. I can see out to about 0.75 microns or 750 nanometers. And what looks different about Earth here? It's got this ozone, and the other planets don't have that. And why does it have ozone? It's because we have oxygen. So plants create oxygen, and which is O2. Ozone is O3. It's a similar molecule, and then just the way the oxygen atoms combine, we'll get both O2 and O3 in our atmosphere. So this is not something that you would predict chemically, but this fact that it is out of chemical equilibrium is interesting. And in our case, it is due to life. And we can start to think about that for other planets. This is a spectrum that was, I think this came out like a month or so ago. It's the first detection of carbon dioxide in an exoplanet. So this is getting to be a pretty interesting molecule, because it is something that we produce. We breathe out CO2. We know Earth has a lot of it, too much. And we can start to then, carbon is important for life, and carbon shows up in other molecules as well. Hubble was able to see water pretty well through in its limited range, but with Webb we have a much longer spectral range. We're able to see carbon-bearing molecules, so and we can see whether those might be relevant for life. So I'm just going to stop here for a minute to see if there are any pressing questions on any of the material that has been presented yet so far.
I don't see any pressing questions in the chat, but you're all welcome to put one in there if you'd like.
And also I could definitely pick them up at the end.
Okay, people are always shy at first.
Okay.
So if you want to keep going, and we'll
all right
again.
I'm happy to press on. All right, so how are we going to do this? How do we do all this great science? Well, it's going to be a pretty interesting observatory. So the Webb has a side that's always hot. That's this side here. This is what we see from the Earth and what the sun sees. So that's the solar panel. It's always lit up by the sun. This is the communication antenna. It's always pointing at the Earth. There's this huge sunshade there that it's got 5 layers. You can see here, this is the flip side, the cold side. It's got 5 layers to let out radiation, and so that the telescope can get cold, really cold, like about 40 degrees Kelvin, which is something like minus 400 degrees Fahrenheit. The telescope is very exposed. There's really no baffle. We just couldn't really afford that in terms of the mass and getting it to fit. And also, you don't want anything that, sorry about that. You want anything that's radiating infrared light. You don't want anything that's warm there. And there's some pros and cons of that. So those are the pros of the lightweight. It's big. So it's 6.5 meters in diameter. That's about, that's a pretty big telescope on the ground these days, right? So that's the size of the MMT telescope in Arizona. I think it's 6.5 meter. The Magellan telescopes in Chile are 6.5 meters. Hubble was 2.4 meters. And as we know, the light gathering power goes as the square. So it's got about 5 times the light gathering power of Hubble. And this was the previous infrared telescope Spitzer. It's got about 50 times the light gathering power of Spitzer, 50 times the area. Now the mirrors are all coated in gold. This is one of the 18 segments. So the primary is made out of 18 segments. This is the secondary mirror that is out here that reflects light. Takes the primary light, focuses the light here, and sends it back through the hole in the middle to go to the instruments. Tertiary is back there. There's a steering mirror that allows it to track. because the whole telescope's really floppy. You can't just move the telescope rigidly and guide it like you can with small telescopes, like with our own telescopes. You actually have to move a separate mirror there. And there's about 50 grams of gold total on the mirror surface. It's not aluminum. I'll get to that in a minute. The mirrors are made out of beryllium. It's not a common element for telescope mirrors, right? I mean, we usually like make them out of low expansion glass, you know, like Zerodor or something like that. But that weighs way too much for something this big in space. Also, we want to have good thermal properties. The Zerodor may have zero expansion in room temperature, but it does change when you make it colder. So they had to be made warm. The mirrors, so the beryllium was like mined in Utah. It was pressed into these blanks somewhere else, maybe Tennessee, and then Tinsley in Richmond. I think they're called something else now. I've got their name somewhere, but they actually polished the figure into the mirrors. They were sent to this cryogenic chamber here in Alabama at this NASA center, and they were measured cold, made warm, measured cold, and then they had to get tweaked up warm to so that their figure would be of acceptable quality when they're cold. Okay, so this goes to the question of why gold. So gold is more reflective than aluminum in the infrared. So it's terrible at short wavelengths, right? Because it looks gold. It's not, it can't reflect blue light. And we see here that longer than about 700 nanometers or so, it's about 99% reflective. And aluminum is less than 98% reflective. It's not that 1% of extra light that's the big deal. Is this property called emissivity in the infrared. And that's the 100% minus the reflectivity. So the emissivity of gold's 1%. Emissivity of aluminum is over 2%. It's a factor of 2. And the emissivity determines how much infrared radiation something's going to give off. So you don't want to be blinded by your own mirror. You know, someone once described that observing the infrared is like observing an invisible telescope is made out of light bulbs. And in the daytime, because the whole sky is lit up too. So you don't want the telescope to drown out the faint infrared signals of your objects. Comparison to the Keck Observatory that a lot of people may be familiar with. So this is like the largest ground-based telescope. It's also apt because it's a segmented telescope. Keck's bigger. There are 2 Kecks. We don't have 2 Webbs. It's 10 meters versus 6.5. It's got about 3 times the area of Webb. It's a little slower. Webb's really fast. It's really short focus, right? Because it has to fit into the rocket. And Webb, as we know, goes to longer wavelengths. 18 mirror segments on Webb, 36 on Keck. Makes sense because like it's a bigger area. Now, segment mass. Each mirror segment weighs 20 times less on Keck, on Webb than Keck, even though these have already been seriously lightweighted. And the mass of the whole telescope is only 6 tons for Webb. And that includes a spacecraft with fuel. In Keck, it's 270 tons just for the rotating part. And so we're really constrained by how much mass we can send into space. And one interesting thing is you figure out how much it costs to operate, if you amortize the construction costs and all that. It's not really all that much more expensive. It's probably a factor of 5 or 10 more times more per hour to operate than a big ground-based telescope like Keck. So once you collect all this light, you need to detect it. You need to focus it and put it somewhere. And Webb has 4 science instruments. So these are like the different cameras that take the pictures. So all 4 of these do take pictures. So we've got split up into these 3 that are near infrared. So they see from about 0.6 microns, which is sort of greenish red to our eyes, out to 5 microns. So that's out to about 8 times longer than our eyes can see. And then the mid-infrared instrument can both take pictures and record spectra. And it goes out from 5 microns out to 28. So really much longer in the infrared. This shows the fields of view of the different instruments on the sky. Again, looking at M51, something that you're probably familiar with. The NIRCam, so this is probably something like 10 arc minutes-ish across there. NIRCam Each of these fields are 2 by 2. They're identical because it's very redundant. We need this instrument to actually, we used it to phase up and focus the telescope. The mid-infrared instrument camera sees this field. The spectrograph can see objects within this field. It doesn't, you can open up like a few 100,000 little shutters here, and you could take spectra of objects that are under the shutters. And this is an imaging, an imager and spectrograph that the Canadians built. It's about the same field as NIRCam. This shows just what one of them looks like. I'm not going to go into all in detail, but NIRCam was built at Lockheed Martin in Palo Alto. And this gray there is its beryllium optical bench. If you look closely on the flight module, it says "Go Girl Scouts." That's part of our outreach. And then all the optics are in the detectors are sort of in these cans. This is what one of the detector arrays look like. These are 2,000 by 2,000 pixel near-infrared detectors. There are 4 of them butted against each other. And there are a total of 10 of these individual detectors in the instrument. And it looks like a mirror image, right? Up and down, because it is. So this is, they're 2 nearly identical modules. There's one up here, and there's another one that is sort of upside down, bolted to the back of it. And then this is just sort of ground support equipment, but there's a similar truss structure in the instrument module in James Webb that it's mounted to. This shows the telescope. It was put together at the Goddard Space Flight Center. That's where it is in this big clean room here in 2016. We're doing instrument test, excuse me, yeah, 2016. I think that's when they did finish it. Maybe they started it in 2014. And we could walk by and watch them put segments in. This is all the instruments together. They were all tested, built separately, and then put together and tested together to make sure they interfere with each other. And the instruments get mounted sort of in the structure that goes onto the back of the telescope here. This shows the telescope, and the instruments are on it here. These wings have been folded back. There are segments on these wings here. And let me actually go back so you can do a better pointer. And there's several segments there. I think there are 3 segments that are folded back, and also 3 over there. So it'll fit into the rocket fairing. Secondary is folded up here. This is the sunshade when it's all out, to be able to shield the telescope from the sun and allow it to cool off. That was at Northrop Grumman down in Redondo Beach. This is now with the sunshade, it's stowed, and so more like a launch configuration. The yellow things are just ground support equipment, sort of helping the telescope move. It was very fragile because it's meant to be unfurled and operate in 0 gravity, but you know, we had to actually test it in Earth's gravity. And this shows the whole telescope and observatory stowed. This gray ring, that's actually the launch adapter ring where it bolts to the rocket. And these are the techs in the clean room down in Northrop in Redondo Beach. Okay, let's talk about the mission. So there are rumors somewhere 1,000 to 1,200 people worked on Webb, and from all of these countries. So it was a joint project between NASA, the US, including Hawaii, the European Space Agency, so they were in for about 20%, and the Canadian Space Agency up here. And also, Victoria, and I don't know, no, sorry, that's Canada there, right? So don't know why they don't have more of Canada in here, but that is Victoria there. And it was launched by the European Space Agency in French Guiana. And that's just where they launch their rockets. It's a great place for launches because it's pretty close to the equator. You can take advantage of almost the full amount of Earth's rotation for getting things into orbit there. This is a schematic showing what it looked like in the fairing. So again, it's a 6.5 meter diameter telescope, and the whole inner diameter of the fairing was 5 meters, and you need to have some clearance because the thing gets shaken a lot and launch. So this is what the launch looked like. This was a great Christmas present. It was Christmas Day last year. It was at about 4:20 a.m. Pacific time. I was up watching it. And it just went off like clockwork. It was just the very beginning of the launch window. Boom! It went up. So this is the Ariane 5 rocket launching Webb. Feel it closely, and there are better pictures of it. You see this little picture of Webb on the outside of the fairing. The Ariane usually doesn't have a camera on its second stage, but the Europeans decided to put one on as they knew this mission was really important. So, which is cool because there's some great videos out there. This is like a still from the video image showing the back of Webb after it got separated from the upper stage of the Ariane. Just a little spring pushed it apart. And this is one of the last images we had of it. And the solar panel has deployed here. So it was really cool to be able to see the actually things happening. And then that was important. Within the first 30 minutes, you want the solar panel to deploy so that you can start charging the battery. In the next 2 weeks, a lot of things happened, all these major deployments. This is sort of how it was launched. And a few days later, these things called, these funny names, there's called pallet structures, like the half pallet structure goes down. And this is what holds the sunshade. Then they get spread out in 2 dimensions. And then the sunshade gets tensioned and the layers separate vertically. And the telescope actually pops up off the spacecraft. And the secondary mirror drops down, the wings fold out. So it's a pretty manual sort of sequence, and we sort of had to do things step by step. It took about 2 weeks, but it went really well. This shows where it is. So it's not orbiting Earth. This is also highly not to scale. So we have the sun here, Earth here. There are these stable Lagrangian points in the Earth-Sun system where you can imagine, like you can understand maybe L1. So about 1% of the distance between towards the sun from Earth is L1. And that's where about the gravity of the sun is about equal to the gravity of the Earth. And the way it works out is that there's another point about equally far away. It's about 1 million miles from Earth called L2. It's a fairly stable point. And if you put an object there, it'll more or less sit there. It might need some nudging. And we orbit some astrophysical observatories around there. It's a nice place because it's very thermally stable. It's away from the Earth and the Moon, but it's close enough to get a lot of light from the sun, and also close enough so it can send data back at a reasonable rate. And that's where Webb is. It's it's doing an orbit of something like I think the radius is about 50,000 kilometers. So it takes, I think, a couple months or so to do one orbit. At the beginning of the talk, I showed what science we thought people would want to do here. Actually started showing what people have asked for and what's going to happen. So this first quarter is exoplanets and disks. About 25% of the proposals that came in and are being, for the first year, are being executed now, are exoplanets and disks. About 25% are stars. One of these are like the physics of stars. The other one is like groups of stars, stellar populations. 26, so 26%, another quarter on galaxies. And then another quarter made up of cosmology, studying the early universe, supermassive black holes, early things, and solar system objects. So it didn't actually separate all that much differently from how we thought it might, from our, at least from our 4 themes. There have been a lot of initial images released. So one thing to keep in mind is that so far, we're just getting the beginning of the science of Webb. It's going to operate for 20 years. So this is like going into a winery, which you'd be familiar with in Sonoma, and getting a taste, and you're getting just like a half glass of wine. That's pretty much what we had, versus getting all the bottles that you're going to buy from the winery and take home and enjoy later. So, but this is a taste. I'll show you some of these examples here in different science areas. This got tweeted just in July. This is supposedly a very early universe galaxy, redshift of 16. To give you an idea, nothing has been seen anywhere near that redshift. Greater, I think Hubble greatest redshifts were something like 10 or 11. But this is an estimate. An estimate, so you really need a spectrum to do the redshift. I showed you earlier, you need to measure the wavelengths of like these known emission lines and then measure the redshift. So this is an estimate made from the colors. And the proof is in the pudding. They're probably trying to measure, or they'll soon try to measure again with the spectrographs on Webb, what the redshift actually is. So, and this shows you how to measure something with a real redshift. This is emission line galaxies. I was on this project. We found 4 of these high redshift emission line galaxies in only about 10 or 20 minutes of test data during the first 6 months. We're just trying to check out the instruments and the modes and do the calibrations. We're looking at a bright star, but just out nearby, there are these other distant galaxies. These are all, we found 4 galaxies with redshift of greater than 6, all in this field. So it's already getting us statistics about the early universe. And then, so these are like common lines. So this line shows up at 500 nanometers is the rest wavelength, but we observed it at over 3.5 nanometers. So that's a redshift of 6 right there. And then this is H beta and H alpha, so that's 65, 63, that's red to our eyes at rest wavelengths, and it's really red at a redshift of 6. Hope you've seen these pictures of Jupiter, just amazing. So these are not real colors. I mean, we can't really represent the real colors anyway, because Webb extends the wavelength range of our eyes, but this is sort of a science communication person put this together with colors just to kind of give maximum information in the image. That's the great red spot, obviously. These are the aurora, these up and down there. There's also like this detached haze you can see on the edge that people don't understand yet. You can see these rings. You can see the rings of Jupiter, which we've only really seen, I think, well, with spacecraft. And then also faint moons. This is actually diffraction of the aurora. So so this is the southern lights of Jupiter there. And just fantastic images of Neptune. So Neptune's small, right? It's usually like less than 2 arc seconds. You can see clouds in the atmosphere. You can see its rings. You can see these faint moons. There's a faint ring here that hasn't been seen since the Voyager 2 flyby. It's the only time it was ever seen. So we can do these long-term studies now of these ring systems around planets that we just couldn't do before. First images of exoplanets. The spectrum I showed earlier was the transit technique, but some exoplanets are far enough away from their stars, you can actually image them. These are in 3 different colors. These are 3 different filters. This is the bluest filter, which is still quite long. It's 3 microns. So that's something like 6 times longer than what the eye can see, and all the way out to 15 microns. And from putting this information together, we've got these brightness points, and you can combine it with the spectra and the near infrared, and this is a model of what's going on in the atmosphere of the planet, the different elements there. So different amounts of carbon, oxygen, water, etc. And this shows how the Webb data are really constraining big chunks of the spectrum. And from this, you can you'll get information which is not available before as to what's in the atmosphere and the majority of the constituents of the constitution of the atmosphere. This one just came out maybe a few weeks ago. This is pretty interesting. So this is a Wolf-Rayet star. It's an evolved star. It's off the main sequence. It's in a binary system. Another star goes by it and have a close approach every 8 years, and that's when dust is being ejected from the extended atmosphere of this Wolf-Rayet star, because it's getting to be like a giant, and it's been enriched in heavy elements. So all of that is real. It's not just like some sort of optical phenomenon. Never been seen before. All right, we're getting close to the end here. I'll say that the orbit insertion was so good, we think we have at least fuel for at least 20 years of operations if all goes well. And there could be other things that could limit the lifetime. You may have heard about micrometeorite impacts. They get impacted about once a month, 10 times a year with small ones. A big one hit in May. And this is like, we can actually take a picture of the mirror, and this is what it looked like after that hit. This is bigger than what we expected, but so far we've only seen one of those. And we're able to kind of readjust the mirror so that it is not a big effect. And right now the mirror is still about almost 2 times better than we thought it would be from this requirement. just to sum up, would like to say a few words about, so what? Well, this is, I think, impactful for everybody because people since the beginning of civilization, at least, have been asking about what's in the universe, how old is it, how did we get here? Are we alone? And I hope that some of these examples I've shown can help show how Webb can maybe address a little bit of this. So we're hopefully see the first galaxies that formed in the universe and learn how they evolved into ones like ours. We'll see how stars and planets form and die. We'll get some idea about how planets and other systems are similar to and different from Earth and solar system planets. And also we had a fair bit of technological advancement. It helped astronomy a lot. It helped just kind of like the whole technical scientific enterprise. The Bay Area, that's where the near-infrared instrument was built. California, which is where the observatory is built, and the mirror segments were polished up in Richmond, and brought thousands of people together over the world. And hopefully the science will bring together more. That's what I have, and I'm happy to take any questions.
Thank you so much, Dr. Greene. We do have a few questions. I'll just start reading them off. How is NASA dealing with the recent problem that impacted MIRI? How does that impact the future of Webb's explorations?
Some people are very much up on this. So yeah, so all these instruments have some kind of mechanisms. You need a filter wheel to change filters. And MIRI has this mechanism in its spectrometer so that you can choose what wavelengths you observe because the detectors are sensitive over a pretty broad range. They aren't big enough to be able to spread the spectrum out. So we have to look at it in 3 different chunks. So that mechanism worked flawlessly every time we used it for over 10 years. I mean, I remember testing MIRI in the UK in the summer of 2011, and it worked well then. We tested several other times cold since then. And but once we launched it and cooled it down, got on orbit, we found it took a little more force than what we thought than what it needed on Earth. And we changed the waveforms to give it a little more force. And we did like probably 100 moves, 150 moves. And then during a science observation, it didn't move when it was commanded. So it looked like it took even more force. So we're concerned there's extra friction in the mechanism, potentially in the bearings. There's an anomaly team that is just about ready to finish up its investigation. We'll probably start we will start observing it again. We will observe the MIRI. So a lot of this as to when is just going to be dependent on how long it takes to implement the fix. And what's likely going to happen is before we always move these wheels in one direction, and the mechanical engineer is saying, no, you should move them in both directions so that you're not continuing to force grit into a bearing surface or something like that. So that's probably what's going to happen. That it's not absolutely settled, and we will have more MIRI observations. I can't hear you, Stephanie.
Oh, I'm sorry.
I think you're muted.
David asked, because the mirror assembly has to be oriented away from the sun, does that mean that Webb is limited to where it can be pointed?
Yeah, that's a great question. So it can only see about 40% of the sky at any one time. It always has to be, so it can always sort of point in the ecliptic poles, because the whole spacecraft can rotate, and it's pointed usually like about 90 degrees away from the sun, but it can trace out a big circle in that 90 degrees, and it can tilt a little bit towards the sun and a little bit further away from the sun. So about 40% of the sky at a time. You can see the poles continuously, which is a pretty small region, and it can see any given spot on the sky at least twice a year for like 2 6-month periods.
Perfect. And we do have some more questions coming in. I just want to make sure you're okay with time because it's 8. Do you have a few more minutes for?
No, I'm good, and I'm sorry for going a little longer.
Oh, that's okay. David also asked, what's the next evolution in space-based telescopes like this?
Yeah, so every 10 years, the astronomers in the US get together and they figure out what they want to do in the future. So Webb was sort of blessed in this community get-together roundtable powwow in the 2000 Decadal Survey report. And the 2021 came out. 2021 is a little late because of COVID, but the next, there are a couple ideas for big telescopes. One is something about the size of Webb, but to work in the visible, have much higher quality surface, be able to look at visible light and shorter light, ultraviolet light, and also be able to look at exoplanets through the current coronagraphic technique. So not like transits like Webb does, but actually sort of like that image I showed you, where you put a little spot over the star, you blot the star out to almost 1 part in 10 billion. So you can see the faint planets nearby. So that's one. Another one is something even further in wavelengths than Webb. So those are two things are going to be investigated in the next 5 or 10 years. And then construction will start. Hopefully we'll be launching in the 2040s for something this big.
That's exciting. That's exciting. Sam asked, is there anything that can be seen only on far infrared? If yes, how much of that part of electromagnetic spectrum can Webb detect?
Yeah, so Webb can see out to what's called, these are subjective terms. Astronomers call it mid-infrared, out to like 20 microns. To give you an idea, that's pretty close to where the Earth and peaks in its temperature. The Earth temperature of the Earth, which is about 270 Kelvin, will have peak infrared radiation around 10 to 20 microns. So that's a prime spot for Webb. That's why we're looking at these TRAPPIST planets that are around similar temperatures there. There are things that only show up at or only bright at longer wavelengths. I mean, there's a lot of dust in the universe. There's a lot of the universe that's only like 30 degrees Kelvin or 30 Kelvin, I guess. There's not degrees Kelvin doesn't make sense. It's that's the unit. So that's like 1/10 the temperature of Webb, 1/10 the temperature of Earth. And that means you need to go about 10 times longer in wavelength. So yeah, like hundreds of microns is where this 30 Kelvin dust is. And that's like regions of star formation. We have these ground-based telescopes, ALMA, which is able to see at these wavelengths. It has a number of huge antennae that can see through windows in the atmosphere. And but we are considering doing a sub-millimeter observatory there for looking at the cold universe.
Perfect. Let's see, Tom asked, will Webb T-scope examine the giant planets and their moons in our solar system?
Yeah, so I hope you got your a little taste of that from looking at pictures of Jupiter there. I imagine also, I think yeah, it was really amazing. I know people are also doing IO. I'm not sure what's going on, but there's a number of people have solar system programs, and that data are probably going to get released into beautiful images as they come out. And they're and I can put it in the chat, but there's a couple websites for Webb. There's like, I think webtelescope.org with 2 B's, webbtelescope.org is one that's got lots of stuff and that gets updated frequently.
Oh, that's nice. That's good to know. Joe asked, approximately how long does it take to observe an exoplanet before you can start to make sense of it?
Yeah, it depends what you want to do. So actually, that's one of the things that I do. We got some observations in the end of September, and to really if you look at almost any new region of spectral range with Webb is going to tell us something. And so even observing a single transit, a 5-hour observation, we are detecting new molecules in some of these planets. So we're learning something there. So, within a period, so it takes, after we get the data down, it takes us a few days to reduce it. And then we have to do this modeling to figure out what's really in the atmosphere. So within a few months, we got a pretty good idea of what's going on. But to really do a fuller inventory of what's in these planets, it takes multiple visits. So it's going to take at least 3 visits of transit measurements to get to like full wavelength ranges with Webb.
Interesting. Joe also asked, is there anything planned for the telescope once it reaches the end of its life cycle, or will it remain in the Lagrange point until it drifts away?
It's going to be there. We don't have anything that can go there. We don't have anything that can bring it back or any, it'll be interesting to see. I don't know if the space billionaires will be having outposts at L2 then, and they could, and the government could sell it to them for their private use, or set it up for tours or what. But and also you really don't want to get too close to it because it's really cold, and any sort of trace gases from a spaceship or people could likely cause molecules and ice to freeze out on the mirror, which kind of absorb in the wavelengths that it sees.
Oh, wow. And it sounds like one of my questions, which you I think answered towards the end, was, does it have a certain shelf life? Why 20 years? But it sounds like the fuel is the main factor.
We will see. We hope it's the fuel. I mean, it's only put a 5-year requirement on it, just because to design something that's going to work that long. I mean, then you have to figure out how many motor moves you're going to have. It just gets really expensive, and very quickly it has to be more redundant. Also, I mean, it's a harsh environment. It's not protected by the magnetic fields of Earth like Hubble is, and there's a lot of high energy massive particles like these cosmic rays that are coming in, also solar flares. We tried to stow it. It's interesting, you have to watch the space weather report to know like what you're doing. Also, we saw that micrometeorites can impact it. So, I mean, we'll have to see. It's pretty redundant. Hopefully we'll get 20 years out of it, but and it'll probably degrade a little bit, but hopefully it'll still be doing great science.
Wonderful. Stephen asked, how far back in time has JW, quote, seen? For example, at what age of the universe are those earliest galaxies seen?
Right. So the ones that we have the definitive redshifts for are, I think, a little further than Hubble. So Hubble could see back when the universe was like 600 million years old. Webb, I think we've seen things that are like 500 million years old. We will have a much better, we think we've seen things that are much younger. We think we've seen things that are 250 million years old, which is really the target of, but we need to verify that because that's estimates from looking at just the images, and we need to spend a lot of time taking that light and dissecting it into spectra. So that's going to be happening within the next year. There's going to be a lot of information probably out by next summer. So we'll be able to have a better handle of that. And then that was actually, I see some of the questions about some of the big surprises about Webb. And it looks like the galaxies, if that's true, if we're seeing pretty well-structured galaxies in 250 million years, then they form faster than we thought. And they got into sort of a more normal structure than we thought they would have from simulations.
Oh, interesting. Let's see, is Hubble going to be replaced by James Webb, or will Hubble still be used?
We definitely want to continue operating Hubble. We're going to have observing opportunities for people to use both because they really complement each other in the wavelength range. And it's, try to get that across with all how things look different in different wavelengths, not only as animals, but it's also, astronomical objects. So they are definitely going to be used together. Hopefully Hubble will last another 5-ish years or so. We'll see.
Okay, great. Could Webb reveal something new on Proxima Centauri B we're not aware of yet?
Yeah, so that one is probably out of the domain of observing with Webb. That planet has been detected with radial velocities. Yet another, because we talked about the transit technique. That's when you get lucky and a planet moves between us and its star, and we see the star get dimmer. Radial velocity, you can actually measure how much the star wobbles when the planet and the star orbit each other. And that is, you don't need as quite as good an alignment. And then there's the direct imaging technique. So approximate B is a radial velocity thing. It doesn't transit. We've looked at times when it should transit. So we probably won't be able to observe that with Webb. Something like that could be a really good target for large ground-based telescopes, for things like the 30-meter telescope, the TMT, that University of California and Caltech are trying to build, and some other countries, or the Giant Magellan Telescope.
Okay. And I'm sorry, Ralph, I missed your question. I'll go back to that one. Does the dichotomy in temperature on the opposite sides of the spacecraft affect its positioning and stability in the Lagrange point?
Mostly not, because it's pretty stable. You know, it was designed to be this way. There is a little bit of an imbalance of solar torque on it, because the sunshade is bigger on one side of the center of mass than on the other. And there's actually a little flap that we use to trim momentum, and then we use fuel to maintain the orbit around L2. So that's where the fuel is mostly being used. It's using to maintain the orbit around L2, which is called station keeping. And then also, as you move around the sky, the way you do it is you spin these wheels. You spin the wheel one way, the telescope moves the other way. It's just conservation making momentum. And at some point, the wheels get a net sort of spin on them, and you have to spin them down by firing these jets that will allow us to spin the wheels down in the other direction.
Okay. Well, we will let you get back to your evening, Dr. Greene. I think that I hit on all the questions. Could you maybe just mention that URL one more time, that where you can see that's continually updated with new images? Oh, there we go.
There you go. So let's go.
Like we planned this.
Yeah. So this webbtelescope.org, this one is pretty good. This is kind of a deep dive. They've got more information on all the individual images that get released. This blog gets updated about once a week, and I think this week they've got that pillars of creation of Hubble versus Webb, and then there's usually like a short blog post here, more information here on the webbtelescope.org, and then there's kind of more history here about how it was all built and everything like that.
Oh, perfect. Thank you very much for sharing that. Well, this was, I think we're all really looking forward to seeing more and more images come out and the science behind it. And I think hopefully you'll be able to be sort of a standing presenter for us for the next 20 years of its life. Once a year.
Well, yeah, hopefully I'll make it that long too, but I'd be happy to give you updates. And I really appreciate your interest. I think it's great that that so many people are so interested in this. I think it is one of the few things in this world that's actually good these days and working well. And thanks everybody for coming out and for having me and for your great questions.
Thank you. Thank you very much. And we hope to see you again next year, and have a good evening. Thank you everybody for joining us and for being here and participating. Thank you very much.
Goodbye.
Bye-bye.